Assalamualaikum warahmatullahi wabarakatuh.
Shalom,
Om Swastiastu.
Namo Buddhaya,
Salam kebajikan.
a greeting of peace for all of us. Good morning, ladies and gentlemen. The Materials and Metallurgical Engineering Department of Institut Teknologi Sepuluh Nopember is pleased to welcome all of you to the 5th International Conference on Materials and Metallurgical Engineering and Technology 2022 held at Research Center ITS. This year, ICOMMET adopts the theme of advancing the role of materials and metallurgical innovation and technology in the digital transformation era to reach a sustainable world.
First of all, let us introduce ourselves as your Master of Ceremonies on this international conference. It is a great honor for me, Faisal, alongside with my partner, Oriza, to be standing here and welcoming you. Before we proceed for today's agenda, we would like to express our sincere gratitude to the excellencies for being here today. Bapak Sigitri Wicaksono, SSI, MSI, PhD, as the Department Head of Materials and Metallurgical Engineering, and Bapak Sutarsis, ST, MSc, PhD, as the Chairman of ICOMMET 2022. Thank you for being present today with all of us.
It is a huge blessing for all of us to gather here at the Research Center in a healthy condition. Thank you to all contributors and participants of ICOMMET 2022 for making this event possible. Starting from the honorable keynote speakers of today, invited speakers, registrants, and all stakeholders.
Thank you to the sponsors who have supported our event, PT Metron Indonesia and PT Garda Multi Solusi Teknika.
Ladies and gentlemen, please allow me to first read the agenda for today. The first agenda are the 3 keynote speaker sessions. Second, 3 parallel sessions and coffee break in between. Third, closing ceremony followed by special performance of UKTK ITS. Then the last agenda will be the awarding session.
Excellencies, after this we are going to have our main session, the keynote speaker session. During the keynote speaker session, we will have an excellent moderator to guide and discuss with the impressive speakers on the interesting topics ahead.
The honorable moderator for today is Bapak Lukman Nurohim, ST, MSc, Ing, PhD. To give you an overview of the excellency, Bapak Lukman Nurohim, ST, MSc, Ing, PhD, received his bachelor degree at ITS, master's degree at National Taiwan University of Science and Technology, and followed by doctorate degree at University of Wollongong, Australia.
In terms of his occupation, Bapak Lukman Nurohim is one of the excellent lecturers at Department of Materials and Metallurgical Engineering ITS and is the former head of postgraduate program.
Other than those 2 aspects, Bapak Lukman Nurohim is highly interested in the following research areas: structure and mechanic materials, electrochemistry, energy storage materials, nanotechnology and nanomaterials, corrosion and failure analysis.
Without further ado, we humbly invite Bapak Lukman Nurohim, ST, MSc, Ing, PhD to the stage. Please give a warm applause.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, good morning everyone. I will stand up here. Honorable speakers, excellent speaker today, Professor Mariati, Professor Patohi, Bapak Sigit as director or head of our department, and my beloved audience this morning. Thank you very much for master ceremony. Already give me time to accompany excellent speaker today to present their idea, to share the knowledge with us this morning. In excellent, in wonderful event that we are heard today, is the ICOMMET International Conference on Metallurgical Technology 2022. Okay, today we have 3 speakers in our audience, and the first speaker will be presented by Professor Mariati from University of Malaysia. Please welcome to Professor Mariati to the stage. Give applause to Professor Mariati. Please sit down. Thank you. This is your mic. Okay. How are you, Prof?
Yeah, thank you. I'm fine, thank you.
Okay, thank you. So when you already landed in Surabaya?
2 days ago.
2 days ago?
Yeah.
Okay. How about the cities? Good?
Yeah, very nice. Yeah.
And what place do you already visit?
Just in the hotel.
Okay.
I will visit a few places maybe tomorrow.
Oh, you will leave tomorrow?
Yes, I'm going to leave on Tuesday.
On Tuesday?
Tuesday.
Or still maybe 2 or 3 days
Yeah.
stay in Surabaya? Okay, thank you. So your recent, what is now you are doing here in USM now?
Actually, now in USM, I'm the Dean of the School of Materials and Mineral Resources Engineering. Okay, I'm doing research on polymer composite. Actually, my PhD was on polymer composite. And then now I shift my research towards the needs of the country. For example, they want us to do research on sustainability.
Okay.
So we try to go into that way, and also Industry 4.0. Okay.
Oh,
So
4.0.
I'll shift a bit my project towards that kind of research. But I still focus on polymer composite because that is my bread and butter. I
Yeah.
like polymer composite very much. Yeah.
So you are going on in USM, right? And then there are many, I've heard here that there are many PhD students in Malaysia interested in your research. So is there any overseas student?
Yes. Actually, USM, we are hub for materials engineering under AUN-SIGNET JICA. So we train students from ASEAN.
Okay.
So I have few students from Myanmar, Thailand, what do you call, Laos. Okay, Laos.
Okay,
Yeah.
yeah.
They studied under this program sponsored by JICA. Okay.
Okay.
So they did master and also PhD under my supervision.
Okay. So what you like to present today in topic?
The
Besides,
topic is on advanced material for printed flexible electronics.
Okay, so okay already
Yeah.
the slide. Okay, audience. So Professor Mariati today will present share the knowledge with us with the excellent topic advanced material for print flexible electronic. So before Professor Mariati will share knowledge with us, so for all audience that give a question, raise question, I will give a door prize. Everyone who raise a question for matter already presented by Brother, I will give free a book, my book, for how to publish in prestigious journal for free to you. This is limited stock, so prepare your question, raise your hand, state your name, and then I will collect this free of book for you. Okay, Professor?
Okay, thank you. Should I stand there or?
Yeah, you can. For committee, please have. Pointer only.
Hello? Okay, so it is clear. Okay, then. So thank you very much. Okay, I'm going to start my presentation. Thank you very much, first of all, to the organizing committee for inviting me to this very great conference. Okay, my name is Mariati Jaafar from University Science Malaysia. My topic of presentation is entitled Advanced Materials for Printed Flexible Electronics. Very brief from where I'm coming from. Maybe you're not familiar, but this is a Malaysian map whereby Penang, I'm coming from Penang. Penang is at the top of the Peninsula Malaysia, where we have, it is near to Langkawi. Maybe you are familiar with Langkawi Island. It is very attractive tourism spot. Penang is down a little bit from Langkawi, so USM, it is located on the island. It is the main campus located on the island. And Penang also, there is another part like at the mainland. The main campus is located on the island, okay? And then the engineering campus, where I'm coming from, it is located on the mainland. It is at the Nibon Tebal there. Okay, so I put the photo there, at the top there, at the right side, that is the USM main campus. And then the down there is USM engineering campus. We have 6 engineering schools in the campus. Okay, so this is what I'm going to discuss or going to present today. The project started, I think, last 4 or 5 years ago, where the industry came to us and then they informed us that the trend in electronic industry where they are moving towards flexible electronic, because now they are using rigid printed circuit board or PCB. Then the PCB is not flexible, high cost, non-environmental friendly production because they are using solvent. Okay, then also it is heavy. Okay, and then they also face problem with waste of rigid PCB. Okay, because we use a lot of electronic products nowadays. Okay, then at the end we throw everything, okay, to the landfill, and then it is difficult to recycle all these PCB because it consists of a lot of materials inside. Okay, they have gold a bit, they have silver, they have copper, they have composite materials inside. Then the recycling process is not easy to be done. Okay, then here it comes, flexible electronic. So this flexible electronic, it is good because it increases functionality, okay, higher connectivity, and more environmental friendly because they use less chemicals if you compare to the rigid PCB, and lower cost because they are using just like a simple polymeric film, and then we printed the traces on that. Okay, then this flexible electronic also support the miniaturization of electronic products or electronic device because now if you can see all the electronic gadgets getting smaller. Okay, last time we have our handphone, it is very bulky, and then now the handphone become very slim, light. Okay, so this is the miniaturization trend in electronic products. So if you look at the flexible electronic, based on the statistic, the amount of flexible electronic is increasing. Okay, that means there are a lot of products. Okay, we use these flexible electronics. As you can see at the right side there are many applications where they will use or they already use flexible electronic in their products. Okay, this is one of the example where the flexible electronic is used in healthcare application, where this printed sensor is used to detect the physiological changes in human body. Okay, then we have strain sensor, where this strain sensor will detect the muscle movement. Okay, and then convert into electrical signals. Then from there we can detect, we can get so many information. Okay. Also, they used to detect blood glucose concentration, okay, by using this sensor. So there are many types of application with regards to this healthcare application. This is another example of application where they use in to detect the food spoilage. Okay, because now mostly they are using use by dates. Okay, they printed the dates on the packaging, and then from there we can detect either the food is expired or not. But then sometimes the food is expired due to the poor storage, okay, during the transportation and so on. But that one we are not able to detect, okay, because we only rely on the date stated on the packaging. This also relates to the waste food. Okay, in Malaysia we have quite critical situation where we throw good food, okay, due to this condition. Then the solution is that they use sensor, they print the sensor on the packaging, and then this sensor basically we can attach, or signal can be sent to the apps in our smartphone. Then from there we are able to detect either the food is okay or not. Okay, so this is one way to reduce the food spoilage. Okay. So when we talk about flexible electronic, there are components that are important. For example, conductive ink. Okay, conductive ink is very important. And then to make it to be used as a patch, okay, then we need flexible polymer substrate. Yesterday I attended one of the presentation. Okay, the presenter mentioned that flexible is very important because it will basically fill the dip and groove, okay, on the skin, and then this one will reduce the loss of the signal. Okay, so flexible polymer substrate is very important in this sense. And then how to produce the sensor? Basically, we need to use different types of printing methods. Okay, actually, there are like screen printing, inkjet printing, roll-to-roll printing. There are so many methods, but in my lab, I'm using inkjet printing. Okay. These are the basic components when we want to produce the flexible electronic. Okay, we need to consider about flexible substrate. Okay, so the flexible substrate, it can be polymers, it can be papers, it can be textile. Okay, then we need to consider active material. To produce the ink, okay, we need to put conductive materials in the solution or in the solvent. Okay, so in this case, normally they are using metal base. Okay, they are using silver. In the industry now, they are using silver ink. Okay, then they also still under investigation about carbon-based nanomaterials. Okay, also they can use conductive polymers. Okay, and then solvent for ink is also important because this will determine the stability of fillers, okay, or nanoparticles in the ink. So in this case, they use either organic solvent or inorganic solvent. And then the printing methods. So this one also important to be considered. Okay, so we go to conductive ink. Okay, so conductive ink is multi-component materials, multi-component system where it contains conductive materials in liquid form. There are so many components inside, like we have solvent just now, either we use water or organic solvent, nanomaterials, conductive polymer, and then they put additive to make sure that the nanomaterials disperse well in the conductive ink. If we look at the number of publication there, the conductive ink, the publication, the research that been done keep increasing. Okay, so in this case, we are interested on graphene, so we try to search the publication related to graphene ink. Then the trend also increase. Okay, so this is the statistic to show that China conductive ink market it also increase. Okay, silver, conductive silver ink, this is the type of ink that being used in market now. Okay, it also still increased, but if you see the carbon-based ink, it also increasing. Okay, when we talk about electrical conductive materials, of course, they are going to select metal-based. Okay, for example, gold and silver. Why they like silver? Because silver, when it is oxidized, it is like a stable. The oxidation is a bit stable if you compare to copper. Copper tend to easily oxidize. Okay, then the conductivity will be reduced. Then the carbon base is now getting acceptance. Okay, because of the low cost. Okay, so if you look at this electrical conductivity chart, we also can use the polymer, conductive polymer, but the conductivity is slightly less. Okay, if you compare to metal base, and also if you compare to carbon base. Okay, so type of conductive polymer that you can use, maybe PPY, PSS, or PANI. Okay, these are the common conductive polymer that can be considered for this application. So the conductive materials, they have pro and cons. Okay, like silver, AGNP, silver nanoparticles, they use it commonly. Okay, then now they are moving towards carbon-based. The one that I put graphene, graphene oxide, and also CNT. Graphene oxide is good because it is stable in water, but it is not conductive. So we need to reduce to make it conductive. Okay, so these are the requirements to produce the conductive ink. The important one is, of course, high electrical properties. Okay, we want to have high electrical conductivity. Long-term stability is also important, because just imagine if we produce the conductive ink, if you want to sell the conductive ink, then the conductive ink will be in store, okay, and then it will be used maybe later on after 3 months or 6 months. So we have to make sure that the conductive fillers is not sediment with time. Okay, so it is very important. And also good dispersion, environmental friendly. Now it is a very there are high concern about environmental. Good addition to the substrate is also important. So during our experiment, we have to make sure that the ink that we produce adhere to the substrate. If not, then you will find out that the signal cannot be transferred, okay, from the ink to the substrate. Okay, then the low cost is also important for commercialization. Okay, so this is the problem that they face now in industry, where the commercial conductive ink, it is expensive because they are using silver base. Okay, then it is not environmental friendly because they are using toxic solvent to disperse the fillers. And also, as I mentioned, also the cost is important. Okay, so in this case, the project that we develop, we try our best to suit with the water-based conductive ink, use of non-toxic additive. Okay, because in the formulation, as I mentioned just now, they use different surfactant, okay, as additive. So this surfactant also sometimes it is dangerous to the environment. So we try as possible, we use a natural surfactant. And then in terms of the substrate, okay, they use synthetic polymer. Then we try our best to use natural polymer as the substrate. Okay, these are the project that we develop. We start with the silver nanoparticles because that's the materials that we use in the market. And then later on, we grow the project into carbon-based, like multi-wall carbon nanotube. And then we go to graphene. And then we try to mix between silver and graphene, because the nice thing is that graphene has a flake shape, and nanoparticle silver is the spherical, that it is attached on the flake shape. Then it is connected. Electrical can be produced, electron can jump from one another, then we can produce the electrical signal. Okay, then we try to fabricate natural-based stretchable substrate. And also we try to improve the addition between ink and the substrate. And lastly, we evaluate the strain sensor. Okay, so we have collaboration with a few universities. Like for sensor part, I'm not expert in sensor, so I work with electronic engineer in that sense. and also we have collaborators from France, Japan, okay, to help us in terms of printing and also develop the ink. Okay, first I will go through very fast. This is about silver nanoparticles. As you know that we can use various type of plants, okay, as reducing agent. So from the literature, there are various type of plants that been used for reducing agent. But in our study, we use Emperata cylindrica. It is like lalang rumput, yeah. So they use this. We use this one for reducing agent. Okay. Then at the end, we produce the silver nanoparticles. Based on the SRD, it is confirmed that it is silver. Then also UV-Vis, okay, the absorption peak is about 400 to 450 nanometer, then it is silver nanoparticles. Then we already studied few parameters, for example, silver nitrate concentration, type of reducing agent, concentration of reducing agent, and also the parameters time, and also what you call temperature during the process, okay. And then this is the SEM for the silver nanoparticles that we produce. The down there is TAM, where we can see the particles that we produce slightly angular shape, okay. And then how to prepare the ink. Basically there are two ways, okay, how to prepare the printed circuit. The first one is by using colloid. By using colloid means once we get these nanoparticles and then we add with the solvent, surfactant and everything, then we are able to get the conductive ink. Okay, then we do the printing process. Okay, another one, because we face problem with the colloid process whereby due to the density of silver, it tends to sediment. So we try to do the printing, okay, at the same time reduce, okay, the silver nitrate. So based on the results of EDX, we found that the Institut methods where we do the printing and reduce, after that we only obtain silver at about 83%, okay. But by using the colloid process, we obtain silver about 97%. So due to the difference in percentage of silver, the conductivity basically slightly lower if you compare Institut compared to the colloid system, okay. But this one can be solved by printing many layers, okay. Printing many layers, then after that you will see that the silver will do the connection, then electron will jump and hook from one another, then the signal can be produced. Okay, so this is just to share with you that we use different type of solvent to produce the ink. Okay, then we check the conductivity, we identify the stability by zeta potential. We identify the contact angle to make sure that the ink adhere good with the substrate. Okay, and then this is the development of carbon nanotube conductive ink. This one also the same. We try to basically varies the formulation. Okay, by using different amount of CNT in non-toxic solvent. Okay, we identify the zeta potential. We identify the viscosity, because to be used in inkjet printing, we need certain viscosity. Okay, contact angle also been measured. Okay, this is the development of ink, CNT ink in water. Okay, so to make the filler CNT stable in water, we need to put surfactant. So there are synthetic surfactant and green surfactant. We try to compare between these two. Of course, synthetic surfactant is well known, perform better. Okay, green surfactant, it is quite new, so we use gum arabic and alkali lignin. Somehow we found that gum arabic is quite good. Okay, it can be used as surfactant based on the stability that been observed. Okay, we try to print this conductive ink on various substrate like PET, paper substrate, TPU, PVA and polyimide substrate. So the addition between the ink with the substrate is very important to be determined. This is also on MWCNT ink. Okay, we measure the effect of different amount of CNT and we measure the conductivity. Okay, this is on the graphene conductive ink. As I mentioned, graphene is good because due to the shape, okay? But it tends to sediment due to the shape. There is tendency to settle down. So we take a photo downside because the solution, it is darker, it is dark, it is black. So when we turn down after 1 month, we found that graphene in deionized water has a very poor stability because it is sediment. But in GR there and PVP, it is quite good. Okay, so there is difference factor. So we identify the conductivity. Okay, it seems like PVP is good. It gives high conductivity. Okay, and also in this case, we print a few layers. Okay, and see what is the effect of printing, number of printing to the conductivity. Okay, and then this one we try to do hybrid between graphene and silver. Okay, we synthesize graphene using electrochemical exfoliation method, and then the silver nanoparticle using chemical reduction method, as I mentioned just now. And then we produce the ink. Okay, and we found that the UVVs, that means the stability, the sedimentation curve is mentioned there. In this case, we use different ratio, okay, different ratio between graphene and silver nanoparticles. Then this different ratio basically affect the performance of the ink, okay, in terms of sedimentation. This is the stability, okay, sedimentation and stability, there is a correlation between these two. Then the zeta potential shows that the different ratio basically will give effect to the stability. Okay, and then this is on water-based graphene, silver hybrid conductive ink. We measure the electrical conductivity as well. From the results, we found that 0.3 and 0.28% graphene and silver shows better stability, wettability, and also electrical performance. Okay. This is the printing process where we print the hybrid ink on different types of substrate. Okay. Then we measure the contact angle, surface energy, roughness by using AFM. Okay. Then it is found that when we printed on PI, polyimide substrate, it shows better addition. Okay. Then electrical conductivity we measured. Okay, this is we study also surfactant adding into this hybrid ink to improve furthermore on the sustainability and also the conductivity. Okay, these are the illustration where when we print more, and then the connection will be occurred, and then the conductivity will be improved. Okay. This is to show to you that when we use different formulation or different ratio between ink, graphene and silver nanoparticles, somehow we cannot put much silver nanoparticles because it tends to agglomerate. So the best properties that you obtain, and also based on this morphology, 0.3 and 0.2 ratio between graphene and silver is the best one. Okay, then we produce the strain sensor. Okay, this is by the help of our collaborator in electronic department. Okay, we put the substrate on the instrument machine. Okay, and then we stretch the substrate. Okay, then we measure the resistance. Okay, then we do it a few times. Okay, we apply stress and we release. Then we apply again and release. Okay. Then this is for strain sensor. Then we found that the resistance, the resistance is sorry. Okay. We measure the hysteresis. Small hysteresis is good because that means the it can goes back to the original condition. Then we see also the fluctuation of the stress that we apply. If it is consistent, then it is good. It is a good strain sensor. Okay, then we measure the gauge factor, okay, for this human motion. Okay, I'm going back, sorry. I saw that they put 5 minutes more, so that's why I'm getting very fast now. Okay, this one also we see the movement of the strain sensor. Okay. Okay, so I want to say here that printing is also important. Methods to produce, to print the ink on the substrate. The one that we use is inkjet printing. Previously, we just use Canon printer. In the cartridge, we remove the, we just purchase the empty one, then we fill in with our ink. Okay, then we have a new budget, then we purchase a slightly better inkjet printer. Okay, and then what I want to say here, the criteria for printed strain sensor, basically we should have ink with excellent dispersibility and stability, flexible and stretchable substrate, good ink and substrate compatibility, okay, and also good sensing performance. So these are the criteria when we want to produce printed strain sensor. Okay, these are what we still continue, a project still continue, where we try to use as possible as we can the material that is good for environment. Okay, so the ink that we produce, the substrate that we produce, we try to use it as green as possible, even though it is not easy, because issue with stability is important to be considered. Okay, and then these are the issues: agglomeration, dispersion, stability of nanoparticle, addition, development of friendly conductive ink, that means no toxic solvent being used, capability of inkjet printer to print the fine pitch. Okay, just imagine when you want to use for electronic application, the lines are very small. Okay, so we need to make sure that the inkjet printer that we use is good enough to print the fine pitch. And also the properties of conductive ink are influenced by many factors. Then it requires optimization to improve the performance. Okay, apart from what I'm doing just now on conductive ink, I'm also studying about face mask layer, where during the pandemic COVID-19, we use masks a lot, quite major. Okay, then we face problem where waste from face mask actually develop, okay, quite a lot on the landfill. So in this case, we try to produce the face mask, the membrane or the layer from biodegradable polymer. So we use electrospinning process. We use PLA and also the new project that we have on PBAT. Then we study about the degradation, okay, in seawater, in river, soil, and also compost condition. So from there we observe, we compare with the PP layer that been used in the face mask. We compare between the two. Then we found that the biodegradable polymer degrade easily if compared to the synthetic polymer, which is PP. And also I still continue doing project on on fiber polymer composite, whereby normally we use fiber, only fiber and polymer. So now I try to introduce nano materials, okay, on the surface of the fiber to improve addition, okay, between fiber and the matrix. Okay, so we use different methods, okay, to produce fibers, nanofillers on the fiber. Okay, and then we are also interested with the hybridization between natural fiber and synthetic fiber, okay, in producing the composite material. Of course, synthetic fiber that really well known, they are using glass fiber and carbon fiber. But natural fiber is good because it is environmental friendly. So we try to use kenaf. Okay, kenaf, we have a lot of plantation of kenaf in Malaysia. And then I purchased jute fiber, okay, from Bangladesh. So we try to utilize, to apply these nano fillers on the surface of the fiber, and we see the performance of the composite materials. Okay, so this is the printing process. That's all. Thank you very much. Okay, if you have any question, then we can discuss maybe during this session or later. Okay, thank you.
Okay, thank you. Give a big applause for Professor. Sit down. Okay, very interesting presentation. And you said in your slide, you said that I point out you said food waste. I think it's very huge for you can say that this can fit for 2.2 million people. And you know, in Malaysia now the population is around maybe 30 million, right? 30 million, yeah, people in Malaysia. But you see, it's in Indonesia also we have a big problem with the waste of food waste. And you know, the amount that we in our capital, in our country is around maybe 1,000 times compared to Malaysia. If Malaysia maybe 30,000 tons, yeah, food waste in annual, but Indonesia I read in online that there are maybe more than 40 million tons only for just food waste in Indonesia. So it's very big problem. Today in many countries they suffer from food. Yeah, many, what to say,
don't have enough food, right?
Yeah.
But in our country, like in Malaysia, we throw the food.
Yeah.
Yeah.
And you know, in Europe now, many them also a crisis energy. So there's still maybe some people are still hungry. Then they a lot depend only for their money for purchasing the energy. So maybe many people I heard. Maybe we can start with the second speaker, and then we can clarify is that true or not. Yeah, is this news in Europe also have a crisis of energy. So Professor, before I give a chance to Adian to raise the question. So what the minimum size of the particle size to use to inject this?
Okay, to be used should be less than 100 nanometer. But the problem is that the particle tend to agglomerate. So once it agglomerates, it will clog the nozzle of the printing process. So it should be less than 100 nanometer.
Less than 100 nanometer.
But it's not easy. I think that's the theory, less than 100 nanometer. But once it is agglomerate, we don't want a very big agglomeration. Because it is stuck at the nozzle, and then the one that come out only solvent. No
This
particles,
is
So we need to control that one. So that's why stability is very important in this project.
So you already start how many years this project?
About 3 to 4 years ago.
4 years ago. Okay, thank you. Okay, for our audience, already raise a question. Only 10 minutes. Yeah, only 10 minutes for the question. Okay, I give you 2 or 3 questions from audience. Is there any question for Professor Mariati? Oh, Tauhi. Sorry for spelling it. Maybe not correct.
Thank you very much for the nice presentation. Am I loud now? Yeah, thank you so much for the nice presentation. Very interesting topic, and we are actually doing some projects which can complement our activities. So one of the questions I had was about, you mentioned about the cost of nano inkjet printing, nano inks compared to silver inks and other type. Any idea on what is the cost difference? And also the follow-up question is about what is the process for the curing? How long does it take to actually become solidified and ready to use, and whether it's causing some issues during the process, because sometimes you have to do many steps during printing.
Okay, yeah, thank you, Dr. Muhammad. Basically, for the cost, I did not calculate, But if you compare to the commercial silver ink, we purchase the same amount of ink, cost about in ringgit Malaysia, 2,000 ringgit Malaysia with the same amount. But when we produce our ink, okay, it is about like 700 ringgit to 900 ringgit. Okay, but of course, silver ink is better at this time because of the conductivity. So for carbon base, we still need to optimize, okay, in terms of conductivity and also the stability. So I can say that the cost of carbon base is slightly cheaper compared to this silver ink that already been commercialized. Okay, that
So
is
only 25 ringgit,
2,000 ringgit.
2,000 ringgit.
And then for carbon base, it is about like 900 or 700 ringgit.
Oh, okay, okay.
It's like a double
Double,
if
yeah.
you purchase the
Okay.
silver ink. Okay, then in terms of curing, when we do the printing, okay, we need to, if you're using silver, we need to do annealing, because to make sure that the annealing means we need to put the substrate in certain in oven, not in oven, at certain temperature. But the temperature we need to control, because otherwise the substrate, the polymer substrate, will deform or will degrade. Okay, so this is another disadvantage of using silver ink on the flexible substrate, especially if we are using substrate based on natural substrate, because they cannot stand high temperature. So by using this natural substrate, then the best thing is go for carbon base. Okay, so the curing is slightly lower. We do not need sintering for carbon base. Just put in oven for certain temperature at certain time, and then that's it. And then it can be used.
Thank you.
Okay, thank you.
Okay. Is there any question from audience? Another question? Keep a door press for the book. Okay. In the back, please.
Thank you. My name is Mafindra. I have a question about what is ilalang. How do we prepare that ilalang is the best materials for the ink? Thank you.
Lalang.
Lalang just now we use as reducing agent. So in this case, yeah. So we just take the Imperata cylindrica, wash in the ionized water, dry for 2 days, boil in water and filter. Okay. Then from there, we use it we mix with the ascorbic acid, okay, mix with silver nitrate and do the processing, and we are able to get the silver nanoparticles. So just process is very simple. Just dry, wash, boil and dry.
Oh, without chop into small piece?
No.
No. It directly.
Directly long.
Oh, okay.
Actually, they use different types of plants as a reducing agent. They also use, instead of plant, they also use fruits as well. Okay, they obtain the ascorbic acid. From there, they can use it as reducing agent. Plant and also fruits can be used instead of using synthetic reducing agent. Of course, synthetic is well known, but if let's say we want our project to be more green, then we can try to use plant and also fruits.
Okay, Mr. Dane. Don't worry about your animal. Still speak this. Professor Mane only just use very small. Yeah. Okay, thank you. Okay, other audience? from audience? Oh, no one, not interested.
We can discuss
In,
later.
oh, okay,
during
we can discuss later because time also only left 3 minutes. So, thank you very much, Prof. Mariati, for your nice presentation. And then next, we give a big applause for Professor Mariati for your presentation. Thank you very much. Before leave, please still stay in your chair. And there is a certificate and token from committee. Is there already? No, they said directly. Hello? Okay. I give back to Mr. Ceremony to conduct this.
Thank you, Professor Engineer Dr. Mariati Jafar as the keynote speaker for the insightful session, and Bapak Lukman Nurrohim as the MSc and PhD for guiding this session excellently as our honored moderator. Thank you as well to the participants for digging deeper and delivering your questions to Professor Engineer Dr. Mariati Jafar.
In great appreciation of our keynote speaker, on behalf of the Department of Material and Metallurgical Engineering and the ICOMMET team, Bapak Lukman Nurrohim, as the moderator, will present a token of appreciation in the form of a souvenir to our keynote speaker with the help of the committee bringing in these souvenirs.
Let's give a round of applause. We hope that Professor Engineer Dr. Mariati Jafar had a memorable time at the 5th International Conference on Materials and Metallurgical Engineering Technology 2022. Once again, thank you Professor Engineer Dr. Mariati Jafar for the insights. Let's give another round of applause.
Moving on to the next keynote speaker session, we will give the stage back to Bapak Lukman Nurrohim as the moderator to guide the keynote speaker session. Thank you.
Thank you very much for Master of Ceremony. Okay, audience, for the next, our honorable speaker is Professor Muhammad Fotohi. Yeah. So, for Dr. Muhammad, please come to our stage and big applause for Professor Dr. Muhammad Fotohi. Thank you. Okay.
Everyone?
Yeah. Okay. Thank you. How are you today?
Okay, thank you.
Already stay how many days?
Yeah, I arrived early yesterday morning.
Yesterday morning. So you will come back to Netherlands directly, or maybe?
Yes, I'm planning to home country in the Netherlands.
Okay. Okay. So, Dr. Muhammad Fotohi, your concern research is about about the composite, right? Yeah. Composite. You say that now you are a director of material health monitoring in TU Delft, Netherlands. Before joining TU Delft, Dr. Muhammad is assistant professor at University of Glasgow and also a lecturer at University of West England. and also he already did his postdoc in University of Bristol Composite Center. So for PhD, you graduate from TUDEF or?
Well, for PhD, it's a long story, but to make it short, it was a joint collaboration. I got the degree from American University in Iran.
Okay.
I did some of the project at Bologna University and Bristol University.
Uh-huh.
So it was jointly awarded project.
Okay. Okay. I have that. You know, Dr. Putu Swarta is our faculty member. You know him in mechanical.
He's already somewhere in the audience, I guess.
Okay. Oh, I see.
So yeah, I met with Dr. Swarta 8 years ago.
8 years ago.
He was doing his PhD at Bristol University's Composite Center, and at the time I was a postdoc.
Okay.
So yeah, we had a lot of good times with him, and it was really joyful, and we have become a good friend.
Okay, thank you. Yeah. So, what the topic right now you want to share with us, Dr. Muhammad? In Spanish, Futuhi or Fotohi? What is
So
it?
it's Futuhi.
Futuhi.
Is the so I think the root comes as Arabic.
Yes,
So
Futuh. Yeah.
that's why some people call Fatuhi, some Futuhi, so it's different pronunciation.
Okay. So, if Futuhi mean in Indonesia is penaklukan. How to say in English? Penaklukan apa?
Someone who conquers in the meaning.
Yeah. Conquer. Yeah.
Conqueror.
Yeah. Conquer. Yeah. In English. Oh, it's very
And my
good.
name is, I think, the most famous name, Muhammad. So
Yeah, our prophet.
everyone
Yeah.
knows,
Okay, thank you, Dr. Muhammad. Please, already the slide and keep to your time to present your topic today. Please welcome. You can stand up here or you can whatever you like. Yeah.
Use the- Come on, drop it again. Hi everyone again. You can hear me, I guess. Alright, great. Yeah, good talking to you, and thanks very much for inviting me and giving me the opportunity, and thank you everyone for coming and attending this presentation. It's an honor to be here and to present to you all, and I've seen some of the interesting works you do in your department, which are fantastic and well done, and hope you can continue the growth of your department. So the topic I have today is on high performance ductile composite technology with visibility of damage. This is a project that I've been doing it for 5-6 years. It started at Bristol University and then continued through my career later on at the University of West of England and then at the University of Glasgow, and currently I'm an assistant professor at the University of Teknologi Delft in Netherlands. So I just need a pointer. Oh, you did it. Thank you. So that's basically a lot of work, not just myself, but my colleagues and collaborators. So I thank all of them for that. So just to give you an introduction about Technology University Delft, or TU Delft, it's I would say the best university in Netherlands, Technology University in Netherlands, and it's one of the best universities in Europe. It has a high population of PhD students, also bachelor students, but they are mainly on technological developments, and it's an engineering school basically. So if we move on here. So this is the Faculty of Civil Engineering department where I am working. So the picture you can see there are some old side and the new side. I'm in the middle, in between. My office is just on the top corner in the old side. And the department is called 3MD, and I'm the Director of Material Health Monitoring. And you may not know, but just as a fact is that we are mostly ranked second in the world. After MIT, our civil department is the second ranked in the world. So it's very prestigious school, and there are many high-level, high-profile scientists working on different aspects of civil engineering materials. Yeah. Right. So here is the topic I'm covering today. It's composite materials Most of you might know, and we had a nice speech from the previous speaker about the materials a little bit at the end, composite materials. What I'm presenting is about synthetic fibers, glass fiber and carbon fiber, and they are epoxy resins as well. So as you may know, composite materials are lightweight and strong, and they are growing extraordinary because of their properties, the excellent properties they have. They have been used in modern aircrafts. More than 50% of the aircraft weight is now composite material. You know, the Formula One car, you have seen perhaps the carbon bikes, and also big wind turbines that they are being developed and they are being used as green resources for energy. So they are everywhere, and we cannot avoid them. Yeah. All right. And some more examples and why the composite materials are great is because they have high strength to weight ratio. Means that you can get a lighter material that can carry more load. And they have got high creep resistance, better fatigue properties. They are good in wear and corrosion, so they resist nicely. And a range of applications that I again tried to highlight and show here with the pictures, you can see there. So, can we go? All right, great. So here is an example of why they have moved toward composite materials. So you see that the modern aircrafts, they have got about 53% composite materials, and the main reason is because when you move towards, for example, carbon fiber reinforced plastics, you can reduce significantly the CO2 emission. So also it takes a little bit more CO2 emission in the production stage, but in the long run, due to less fuel consumptions, you would get better return because you are using less fuel, it's cost effective, and it also reduces the CO2 emission, which is a big challenge currently in the environment. And of course, you get better fatigue and corrosion resistant property, and that extends the lifetime of the structure as well. All right. However, a big challenge with composite materials that are being used currently in industry, for example, glass fiber and carbon fiber, is that they fail catastrophically. They fail suddenly. So you see the video that is being played is a carbon bite frame. There is no visible sign of damage. It doesn't show any warning, and it just snaps quickly. Suddenly it fails, and you see the result. And that's why, for example, many people don't use carbon fiber bikes, because they are not safe enough for many applications. And you can widen it to other areas, you know, the aircrafts. Imagine you have a problem with the aircraft that is made from carbon fiber, so it can snap and it can fail, and you will not be able to control the failing process. Or similarly in other applications. So as a result, what they do, they over-design the structure. When you are over-designing a structure, I talked about the lightweight, then you are increasing the weight. Then you need expensive inspection process, and these are not all good. So in our projects, we are trying to minimize this problem. If we go to the next slide. All right, so you see this is an example of a metallic bike. So you have the steel bike, and you saw the carbon fiber bike in the previous one that failed. In the steel, you have a nice plastic deformation, and it doesn't fail catastrophically. As a result, you can control this process. This is like the project we were trying to have high performance ductile composites. Composites are brittle, we were trying to make them ductile to fail similar to metallic materials. And then we can avoid the catastrophic failure and move towards ductile failure, which is more controllable and gives you an early warning. Yeah. So here is an example of how the materials fail. You see in your left side, we have the stress strain curve for a quasi-isotropic carbon fiber composite. It's stiff and strong. It can tolerate much more strength. However, when it comes to the strain, it's quite low, and also it's just a straight line and it fails. Whereas in the aluminium one, you see that there's a nice plateau stretched over a wide range of strain, so it doesn't fail catastrophically, and you can see what's going on. And the purpose of our project was to make the right side picture where we can get a non-linear behavior from composite materials. We call them pseudoductile materials because they are not really ductile, but they are designed to have that pseudoductile behavior, the non-linear behavior. And I'm going to elaborate how we have achieved those non-linear behaviors in the latest. All right, here is the way we have achieved this. The challenge we had, we tried to use the design in our process. And how we did that? We tried to use thin ply hybrid laminates and demonstrate stable failure, the failure that can be tolerated by the structure. You can see from the picture in the left, you have different damage failures. We call it delamination and fragmentation, that is shown with the red. And it's in the hybrid of two different materials, thin ply and thick ply, low strain and high strain. And when you are putting that under tensile, you get the graph, stress strain graph in the right side, where you see a linear behavior, then the non-linear area, and after that you have the continuation of the load that is carried still, but the same material that is being damaged, but it can tolerate the damage. Right. And here how it works, you have a high strain material, a low strain material, they both work with the same behavior, a linear catastrophic failure. Okay. If we combine them and if we hybridize them, we get this pseudoductile behavior, non-linear stress strain curve. Can we move on? All right, but not all the hybrid materials are going to produce that behavior. So in order to get that behavior, we need to design the material properties and also the thickness ratio and all the other parameters in a way to produce that behavior. You see that we have identified 4 types of failures. The conventional hybrid materials usually fail either as a premature failure or as a catastrophic delamination number 1 and number 2, which are not desirable. They are catastrophic failures. We don't want them. We want number 3 and number 4, which we have designed to fail like that. This delamination and fragmentation, but the damage can be tolerated by the layers. Alright, if we move on. Okay, so you see, this is a design tool we have generated. It's an analytical design tool that is developed in our group. And it shows, for example, here 2 types of materials that is being hybridized, glass fiber and carbon fiber. So the yellow one is the glass fiber, the color, and the sort of the brown one is the carbon fiber. And after we hybridize them, we can see the carbon to glass ratio and carbon layer thickness. So we can find where is the optimal damage mode map we should be using, which is the red area that you can see. And you see that the way that the material is behaving if we change these parameters, the carbon to glass ratio and the carbon layer thickness. And you see the graph we have, a stress strain graph, shows how these materials is going to behave if we have different type of process for the selection of the hybrids. All right, this is the experimental result for one of our case studies for stress strain or stress extension, where you have a nice linear area that you see in most materials, carbon fiber or glass fiber or composites and many other materials, and then you get the plateau that is the damaged area where the fragmentation and local lamination are happening, and at the end you get extra load carried because your laminate still can carry the load. It's not totally degraded and it has not loosened. And then you have the final failure at the end of the extension. All right, great. So, and 2 other examples and application like that we also did tensile test design for them, stress strain. You see that the graph on the top left shows that we have S-class, MR40 S-class. So that's one type of carbon and glass that are sandwiched, and also T1000, another type of carbon. And we have managed to produce that non-linear behavior or pseudoductile behavior that we wanted from the design of the experiment. Similarly, in the right side graph, the stress strain shows that we have a carbon-carbon sandwich that is being used. So, meaning that we are using the two type of carbon, not glass and carbon, two type of carbon with different strain to failure to produce that non-linear behavior. And one of the interesting aspects from this was the change of color. So, as you can see from the pictures here, these are the pictures in the lower side. These are the pictures that we have taken by a normal camera, and you can see visually. So the one on the top that is totally black is a specimen that we manufactured in the lab. It's carbon and glass hybrid. Initially, the hybrid is black, fully black. But when we increase the strain, what happens? We have fragmentations and then delaminations. But white areas, the white areas that you can see, the strip patterns that you see, they start appearing at a specific strain level, and that's a strain to failure of the carbon, low strain material. And you can see that that can be used as a sensor. As a sensor that you don't need any electricity. It gives you an early warning just by watching at the structure without needing for any strain gauge or any other device that you need to electronically do that. So that's an interesting phenomenon that we observed, and we then followed on that. Okay. So far I discussed about hybridization, and we talked about hybridization of unidirectional materials. But in reality, in practical applications, what happens is that you put the fibers in different directions. For example, you put them as quasi-isotopic laminates, where you have the fibers in 0, 45, minus 45, and 90 degrees, or other type of quasi-isotopic laminate. And the challenge we had was one of them how we should mix these type of hybrids in order to get the pseudoductile behavior. And there will be new challenges, because when you have multi-directional materials, there are other type of failures, such as pH delamination that is happening, and we wanted to avoid that, because otherwise we wouldn't get that behavior. So we then focused on two parameters. One was the stacking sequence, and the other one was the fiber type, and we tried to come up with optimal solutions using the design and design parameters, analytical solutions, and finite methods. I'll explain here. Okay, so we have two type of stacking sequence here. The colors are the material types. So you see that in one of them, we call it material dispersed. The material is dispersed between, in the hybridization process, and you have a quasi-isotopic laminate that has blocks of materials that are sandwiched. And in the other type, layup number 2, we have materials blocked. We have one type of material that is making half quasi-isotropic, then we have the other type of material and that other half, and then you have the symmetry line showing that it's a symmetric layup. Some of the terminologies you might not be familiar because of the background. You might not have the symmetry line is because you have to have a symmetric composite in the process mainly. All right, so we have the orientation. Now we have colored the orientation here. Now we have the thick block of materials. So thick blocks of the angles that we are not willing to have, because it's like a thick ply laminate, and we choose to go with layup number 2, which is orientation dispersed with thinner plies in different directions. So Okay, this is a result of such design we have achieved. This is for quasi-isotropic 60 and it's glass and carbon. T800, TR30 carbon and S glass as the high strain material. We have this is strain curve. And what we did here was actually we tried to load the samples in different directions. We tried to not only load them in 0 direction, but also in 60 and minus 60 direction, because in real life you would expect different type of loading conditions in your composite structures. And that's why we did, and we managed to get nice pseudoductile behavior in all the directions. And you can see the pictures we have taken from the damage process, just simple visual pictures. The lamination and fragmentations are visually observed, and our design tool, which I explained about, the analytical design tool, can also predict this design nicely. Well, another interesting area that we looked at was the notch sensitivity. As you may know, in most materials that are brittle, sensitivity to notch is a big challenge. And as a result, when you have a hole or sharp notch, then they fail at stress levels much earlier than what they are designed to, because there's a stress concentration and they have sensitivity to that. And then they fail earlier. In an ideal brittle material, 0.32 is the notch sensitivity factor. And in a ductile material, it's 1, it's good. It's not sensitive to notch and holes. So what we tried to do, we tried to put some holes and notches in our samples in the pseudoductile composites and see how do they behave. We will see that in the next slide. So you see, here are the results of this multi-directional composite materials that we put them under a test for notched and open hole conditions. And we have managed to get a notch insensitive behavior much better than like the traditional composites. You see the picture here in your left. The blue dashed line in the lower side is the failure for like a brittle composite material, and we managed to get to the top blue line, dashed line, where we almost exceeded the notch sensitivity, and the notch sensitivity somehow disappeared. And one of the interesting points from the pictures you can see on the sample is that when you are increasing the strain, you actually see that the color of the structure is changing. So you can see visually that there is something happening. So you can prevent that. That's sort of an early warning, structural health monitoring system. And we also did put these on, for example, fatigue test to see whether they will be okay under fatigue loading condition, which is what happens in reality. In application, you just don't design for one type of cycle, you design it to last for a long time. And we managed to get this same behavior in quite high strain load levels, because it's difficult to actually avoid fatigue failure, because it will happen, but the question is how long it will last. And we managed to actually get decent result when we had these hybrid behaviors. As you can see some of the result, that when we increase the stress level, then we get failures, but they are not also catastrophic, and they happen gradually. So again, we have this damage that is happening, but it's tolerable and it can be controlled. Yeah. Also, one of the areas that we looked at was the compact tension, because in aerospace industry you get lots of shears that are perpendicular to the direction of fibers, and we wanted to see how these hybrid composites are behaving. You see the picture in the left showing the green, which is a conventional composite material. As you see, the stress and displacement is the stress level is much smaller for the pure carbon, and we get the behavior that is quite similar to the glass, and these hybrid materials work nicely in the compact tension. And we used acoustic emission to also monitor the damage stuff, and we realized that we get damage much earlier than what you get in the glass, but those damages are not significant and they are tolerable. Okay, if we go next. Similarly, bypass bearing is a standard test that is being used in aerospace industry for bolted structures. And again, we get much better behavior using our hybrid materials. If you look at the blue line, is the hybrid material, and it behaves, it all performs the carbon fiber materials, and you can see the results on how these type of materials have failed. In the picture there is that with hybrid composites you get more ductile behavior compared to conventional carbon fiber composites. Alright, I briefly talked about what happens when you have these hybrid composites. They change their color, and the color change is just because of the failure that is happening in the hybrid structure. And you can visually see that, so you don't need anything else to see. You just see, okay, there's a color change. Okay, this can be used as an early warning, for example, for overload behavior in the structure. And if you go, okay, you see, one of the advantages of this sensing is that I have tried to show a schematic in the picture below, where you can actually attach this as a small sensor on different type of structures, and that shows the color change, and you can actually attach that in different directions as like a strain gauge, that you have the russet strain gauge that you put in different direction, and it shows the color change, and you can see whether your structure is okay or not. And the good thing is that it's wireless, low cost, lightweight, requires no training, requires no energy, and you can just simply attach it as a warning on different structures. Yeah, we demonstrated this technology on a bike handlebar. You can see the bike handlebar, if you have exceeded the load level that is supposed to tolerate, but still in the design load, you see the load that we applied is the sensor activation, and the standard load that they should supposed to tolerate is much lower than that. So we just wanted to make sure that we are not activating the sensor much earlier. So we designed them to get activated at the higher load levels, and we were using that as a safety factor, that if someone sees that, it means that you have put too much load on your bike, for example. And this can be applied for other applications. Yeah. This is an example where we use these composite materials to repair some aluminium panels. This is again normal practice in aerospace industry, where they use composite materials to repair aluminium panels. And if they have a crack, then you cannot see that in normal repair using composite. But with our repair, with our composite materials, you see that when the crack starts propagating, we can visually see the size of crack. And that's crucial for non-destructive testing, because we know what's going on in the structure. Yeah, if we move on. And similarly, we can use this hybrid structure for fatigue life monitoring, because the number of cycles, you increase the number of cycles, there's a more delaminated area in your structure. And then you can correlate that delamination area with the number of cycles, and from that you can use that as a simple way to monitor fatigue life of structures. Yeah. Another application that is very important in composite industry is barely visible impact damage. You know, the damage that is happening in composite materials are usually hidden. An example is shown in the picture in your right, where you can see in the lower side, we have a huge delamination detected by CS scan. However, we don't see any damage that is visible on the surface, back or front surface of the laminate. But in the upper side picture, we have the delamination inside the composite. But with our sensing technology, we can actually visually see that it has been impacted and it has damage inside. So that's somehow correlating the outside damage to the internal damage using this technology is also an interesting area that we are looking at now. Right? To conclude, we had a nice ductile hybrid composite developed, notch insensitive and good behavior in different applications and loads. And overload sensing up a concept that is an interesting area to look into. So that would be good to follow up and do further research in this direction. And if we go, this is the last slide I have. If we go one more. Yeah, well, I would like to thank my colleagues and also the organizers of the conference who have given me the opportunity to present. EPSRC Engineering and Physical Sciences Council at the UK, where they funded the project, Field that has helped me to perform some of the activities in the work, and also I'd like to announce that I would like to also get to have more collaboration by MS and PhD leadership opportunities we have in the team, and also try to be more in contact and hopefully find ways to cooperate and communicate more with the center, with your center and also others. And yeah, thank you so much for the attention, and I welcome if you have any questions.
Okay, thank you very much for a nice presentation. Give a quick applause for Dr. Muhammad. Let's begin. Yeah. Before we give a chance for the audience to raise the question, so Dr. Muhammad said that where you got the supplier, I mean the carbon or the fiberglass, this is for local or you import for the material?
So the type of material, is it imported, you mean?
Yeah.
Well, we had some manufacturers in the UK, they were manufacturing, for example, we had Hexcel, that they are manufacturing glass fibers. For the carbon fibers, they are mainly made by a Japanese company and a Swedish company. So yeah, from different, all around the world. Yeah.
Okay.
But of course, one of the areas that I am now looking at and I'm keen to follow is the use of natural fibers, hybridization using natural fiber composites. Because if we can use natural fibers in the areas that are less impotent and use some other type of materials that are stronger, so then we can hybridize it in a way to use the most of materials. Because the stress is not uniformly distributed in the structures, and we can optimize it by the distribution, and this is called topology optimization, where you can reduce the material in different areas.
So as long as you already applied in commercial product or not?
These are, so the project I'm working, it's been collaboration with 9 industrial partners. So, Rolls-Royce, then we had BAE Systems, we had the National Composite Center in the UK and a few other big companies. So yeah, there are, for example, some demonstrations in gas cylinders for this limit detection sensor. So yeah, there are some works going on, but as you know, these are low technology readiness research, and to go through the technology process, they're increasing the readiness level. There are some works to be done. So these are fundamental research with applications that we have demonstrated. We call it TRL6. But in order to go to TRL9, there are still certification process and other parameters that needs to be done.
Yeah, okay, thank you. Because in your slide you saw many is like a bicycle, and we know that Netherlands people love cycle every day. Yeah.
Yeah, too many bikes.
Yeah, too many bikes in Netherlands. Maybe you can import Indonesia. Okay, thank you for your presentation. And okay, for who already just comes to this event, I will give information that whoever raise a question from the presenter, we will give you a book, a free book. Yeah, and this one for you free. And this is how this book is how to publish in international journal. Okay, please, audience, is there any question? Okay, please. Another one. Okay, two. Okay, please first. State your name and your university.
Doesn't work.
Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Um,
The name, please.
yes, I have the same name as Dr. Putri, but just the front name. I'm Muhammad Ikhwan Najmi.
Okay. Muhammad
Yes,
Irfan.
Muhammad Ikhwan Najmi. I am from State University of Malang.
Okay.
Yes. Actually, I am the bicycle user. From maybe most of my life I ride bicycle. Yeah. Yes. So I'm very interested about this research that Dr. Putuhi doing, and maybe so that the research that has used by many company. That we know that ITS was one of Asia Pop, right? Yes. The ITS have the electrical motorcycle that guess it? Yes, sir.
Yes, yes.
Yeah,
Yeah.
guess it.
Okay.
Is it that they have a bicycle that made by Teknologi that has have a branding by Teknologi.
Yeah, that's a good question. I don't think they do. Because they're bicycle lovers, and I think there are a few companies that they do commercial, production for bike, but I don't think there is a brand by Teknologi.
That's right.
We do have like student projects, like they do participate as this, this racing car, like other type of projects that they have. But as we are not a commercial entity, so I don't think they do.
Then maybe I want to volunteer if it can produce. I want to be a
Yeah.
tester.
Yeah, I mean that's something. We have lots of startups from TDL, where, for example, if you have a good idea, a commercial, viable idea, then there are procedures to be followed, and you need to write a business plan, and then. But there are some very successful spin-outs from the university that they are now doing very well, and one of the projects, and I'm actually thinking of working more and hopefully commercializing, is in line with what I presented by slightly different concepts, which I cannot reveal because of the IP issues. But overall, there are a lot of interest from the industry. If, for example, you see these sensors can be used in infrastructure, there are a lot of areas that you want to monitor, make sure that they are not going to fail. We have got lots of, I think, natural disasters happening here, so your infrastructures must be safe. The bridges, the buildings, and different parts that you can use this type of technologies. So I see a good, business case for it.
Okay. Your question?
The question is that as a bicycle user, that I have the last bicycle that I use now. It has it was 10 years old.
Mm-hmm.
It was 10 years old. That the handlebars already have the like a corrosion, that not the corrosion, but the internal material has some change, some color change.
Okay.
That is that some sensor. Sensor is that sensor. Is it can be used at the bicycle that it's it's not produced by Teldelf, that we can have the sensor to use at our bicycle. Maybe that.
I didn't get the question exactly, but I feel so. Your question is that can we use the sensor to sense the status of the bike? The answer is yes. It can be. I mean, that was just a simple example that people can understand. There are more critical structures that we must make sure that structure is safe. You know, sometimes the bike is also a challenge. It may fail and it can cause failure and problems associated. But imagine a hydrogen tank that is under pressure. You need to make sure that it's not over exceeding the strain limits, and many other applications. So yes, these type of sensors can be calibrated to be used for different case studies. So yeah, but there is a process to be done in each case. It's not simply using what we have already developed, but rather using the knowledge and the technology to adapt to the applications.
Okay, thank you.
Yes, thank you.
Okay, thank you. For the second question, please. Maybe the last.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone.
Okay.
Thank you, Dr. Futuhi, for the excellent presentation. And I want to ask about...
Please, the name and university.
My name is Harith Muhammad Taniswara from ITS. And I want to ask about the composite. We know that based on the reinforcement, the composite is there are three types, like laminate, fibrous, and particular. And correct me if I'm wrong, the composite is laminate that you presented. And the question is why you choose this type of composite, laminate, and is it effect of the sensor or the application? And why don't you use like a fibrous composite? Thank you.
Yeah, well, thanks for the question. The question is why just one type of materials that you use. Well, to clarify, yes, there are continuous fibers, short fibers, and also particle reinforcement. However, those type of short fibers or particle reinforced can also have different layers. So they can have laminates one on top of each other. So that's called laminated composites. They are mostly made not one layer, but more than one layer. So actually we did use some short fibers where we also generated the pseudoductile behavior. So you can generate the fibers to be in different directions and get the strengths. What we did there, we also aligned the fibers. Fiber alignment is also another technologies that is being used, because if you align the fibers, you get better performance. And one of the reasons for and the motivation for the choice of continuous fiber mainly and this type of material was because of the application. We were targeting aerospace applications where you need a high performance. Usually when you have particle reinforced composites or short fiber composites, you are reducing the performance of the composite and they don't have the strengths you need, so they are not as strong and as good as this composites that I showed. However, for other applications, for like automotive application or many other applications, those actually are better, cost effective and can be used.
Okay, thank you. For the next question, the next participant who raised the hand, the white shirt. Okay, I give you a chance the last time for the last question. Please, name and the university from.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Afaro. I'm an undergraduate student in Material and Metallurgical Engineering. I would like to ask about the visual color changes in the ductile carbon laminate. So in industry, most of the material used is being coated for environmentally protection and aesthetic mostly. If so, then the advantages of the carbon dichloride is loose. So you cannot inspect the visual color changes when it's coated, right?
Yes, very good question.
Yeah. So I would like to hear your thoughts about this.
Yeah, so if you have a coated structure, because you're not always putting them as in the manufacturing process, you can put after coating, that's one, or it can be used as a coating, because there are applications that they use composite as a final finish layer because it gives a nice texture, and there are examples in some applications that are being used, automotive or few applications, so it's actually a cosmetic appearance as well, so that can be used. Also, these sensor designs can be used in a way that can peel off the paint. If you design these type of failures, it still could be tolerable, but they can snap, so they can peel off the paint and you can see that. So there are different type of designs that now I'm working on, that you can peel off the paint, and then you are visually seeing that, okay, that area has been damaged, and it pops out.
Okay.
Thank you.
Okay, thank you for your lesson. Thank you for your response, Dr. Watahi. And thank you very much for your attention. Big applause for Dr. Muhammad. And then because this time is up, and then I will forward back to Mr. Ceremony for the next. Okay, we are waiting for the.
Thank you Associate Professor Muhammad Fatohi as the keynote speaker for the eye-opening session, and Bapak Lukman Nurrohim for guiding the session excellently as our honored moderator. Thank you as well to the participants for digging deeper and delivering your question to Associate Professor Muhammad Fatohi.
In great appreciation of our keynote speaker, on behalf of the Department of Material and Metallurgical Engineering and the ICOMMET team, Bapak Lukman Nurrohim as the moderator will present a token of appreciation in the form of a souvenir to our keynote speaker with the help of the committee bringing in the souvenirs.
We hope that Associate Professor Muhammad Fatohi had a memorable time at the 5th International Conference on Materials and Metallurgical Engineering and Technology 2022. Once again, thank you to Associate Professor Muhammad Fatohi for the insights. Let's give another round of applause.
Moving on to the next keynote speaker session, we will give the stage back to Bapak Lukman Nurrohim as the moderator to guide the keynote speaker session. Thank you.
Okay, thank you, Mbak Oriza. Yeah. Okay, ladies and gentlemen, honorable audience, this is the last our speaker, keynote speaker today, and the last speaker here will be presented by Professor Sungging Pintawantoro. Please welcome Bapak Sungging Pintawantoro. Big applause for Pak Sungging. Oh, yeah. Okay, Mr. Sunggeng is my colleague in our department, and he will tell about the recent research now. What the recent now, please, Pak Sunggeng? Recent research.
For the last topic in our laboratory about the red earth extraction.
Red earth extraction. Okay, very interesting. Because we know that our country has a lot of resources, like mineral mining, and then this is our concern now. And in the Pak Sunggeng labs, now they are doing some research about how to extract the rare earth element from our natural resources. And for today's presentation,
Green and environmentally sustainable iron making.
okay, so for today's, Professor Geng will be present about the iron making process overview especially in Indonesia. Please welcome and big applause for Mr. Sunggeng. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good evening. Thank you very much, Lukman, and welcome in ITS for Dr. Foti and Dr. Mariati. Nice to meet you in Surabaya. I want to share this evening about the green and environmentally sustainable iron making for Indonesia. Of course, this title is inspired by the spirit independency for iron and steel making in Indonesia. But as we know that the big issue now is about the resource, the energy, and the environment. So this is why I will share the overview, the several technology, or several method to how to build the green and environmental sustainable iron making. As Indonesia's GDP on average 1.6 million, that means the magnitude of Indonesia GDP, industrially developing its infrastructure, and thus the Indonesia iron and steel consumption is continuing to increase. So that's why this progress is correlated to the consumption production in national level. So, as we know that the role of steel is, in particular for structural application, is still irreplaceable by other material. So that why the steel is still important for our nation. And then the other hand, the higher steel production in the country, as we know that the emission of the CO2 will produce and will increase as well. So that's why it is important to how to reduce the CO2. As we know that the iron and steel industry sector contribute around 7 until 9% of the total CO2 emission in the world. And the process of producing iron and steel can be done by through two main routes. The first is the blast furnace precipitation, PF, and the other route is the direct reduction, iron and electric arc furnace. The abbreviate is DRI-IEF, and the blast furnace route is widely used in steel production. It's about 70%, and for the DRI-IEF contribute about 26.3% in the steel production. So, based on this outline, the article aims to provide overview of the process of iron working in steel in Indonesia, especially in the ASEAN region. How to realize the process of the iron working in environmentally friendly and sustainable for Indonesia. This is the statistic iron steel in ASEAN region. You can see that the Indonesia is in second place in ASEAN. The number one is Vietnam. But if we look the people in Indonesia, I think is higher than in Vietnam. So that's why I think it's, in Indonesia we still need the more consumption about the steel. So, but but we have to choose the role of the steel industry in Indonesia. If we review about the iron manufacturing process, as I mentioned in previous slide, there is the blast furnace route. Actually the blast furnace route is vertical reactor, the function for the smelting process of iron ore. And blast furnace is still most widely used process. As we can see in the reaction occurs inside the blast furnace, they use reduction of CO gas, and the product for reduction reaction is the CO2. So that's why in iron and steel making contribute 7 till 9% in the world. Even not in Indonesia actually, but in other country. But if Indonesia want to build the steel industry, it must be consider this situation. I mean, from the conventional blast furnace. The iron manufacturing process is direct reduction iron. It is shipped in DRI. The DRI process is with operating temperature below the melting point, and material fed in the DRI reactor to reduce the iron oxide to metal iron. So in the reduction process can be done by applying the reducing agent in the form of the CO gas. So the product of the DRI process can be in strong iron, direct reduction iron, and hot briquette iron. In their IF route contribute what 26%, and the other PF route. But in Indonesia, their I product is only about 3.9%, and the pike iron, I mean the blast furnace route, is 96%. For the chart, we can see that the comparison of pig iron and the product in Indonesia is now dominated by the pig iron product. Yeah, the other process is smelting reduction. Smelting reduction doesn't use the metallurgical and doesn't use the pre-agglomerate material smelting reduction. So if we can see in the figure, there is the technology from the FINEX process and correct process is based on the smelting reduction process. So we can see that the fine ore is not agglomerate. I mean, in blast furnace conversion, usually fine ore is going to the sintering to make agglomerate before entered to the blast furnace. And for the FINEX process, the fine ore is reduced in the fluid dispatch reactor. And then, yeah, there is no non-coking coal. There is no coking coal. That means in the final process, we are not use the coking coal to make the coke. But in the conventional blast furnace, we use the sintering and conversion. This equipment, this process is produce more CO2. So I think the FINEX process, I think the more environmental friendly than the blast furnace process. Also in the correct process, yeah, there is no agglomerate and coke making, just the reduction process in the sieve process, and then melting in the melter gasifier furnace. Yeah, this is the difference between FINEX process and the correct process. In the FINEX process, you can see there is the 4 reactor to make the reduction process, but in the correct process is only 1 reactor to make the reduction process. So from this situation, we have to make effort that can be generate environmental sustainable iron making in Indonesia. The first is we can use biomass. So based on the life cycle assessment study, the use of biomass can help mitigate CO2 compared to the use of fossil fuels such as coal or coke. Then the use of biomass is estimated is to reduce about the 54% of CO emission in the BF route. Yeah. Because the BF, as we know in the previous slide, the BF route is 70% in the world. I mean, to make iron making. And biomass that can be used in fuel substitution in the BF route in the form of the charcoal. If expanded furthermore, biomass can be used to substitute coke both in the step of coke making and sintering in the blast furnace. Yeah. So as we know that charcoal can renew, but the coal cannot renew. So that's why this is, I think, is more environmental, and then for the resources can be renewed again for the charcoal. Actually, this is back to the in the preliminary in the first iron making. The other effort is using the hydrogen in iron making. Yeah, even the other application, the hydrogen is now most interesting in other application as well. So they use hydrogen gas in iron making process to reduce the CO2 emission. As in the previous chart, in the conventional blast furnace process, the reductant is the CO gas. But the CO gas we can substitution with the hydrogen gas. So the product from the reduction iron ore with the hydrogen is the water. I think water vapor. So that's why this is more environmental friendly than the CO reduction. The product is the CO2. Yeah, to significantly reduce the CO2 emission, the FS work it need to modify. That means the modification by injection process of hydrogen into blast furnace through the bottom part of the blast furnace. So that means the hydrogen can substitute the function of the CO gas. And yeah, from the according the Yilmaz et al, with the injection hydrogen to the blast furnace can reduce the 21% of the CO2 gas emission. Yeah, the other effort is using the alternative raw material. Yeah, the first is the scrap. As we know, especially for the DRI process, the raw material is using the scrap. The scrap reprocessing contribute to about 24% of the wet steel production. Yeah, and the DRI process which contribute about 5% of the wet steel production. And the use of steel scrap reduces the approximately 1.5 kilogram CO2 per 1 kilogram of processed scrap. And in Indonesia, scrap is still needed. It's about 60 steel company with a total capacity is about 9 million tons per year. So of this last percentage, around 60 to 70% still rely on the scrap is imported. Yeah. Yeah, recently many steel industry is having difficulty to get scrap, raw material for the steel industry, especially in East Java. So that is the problem now happen in East Java and also in Indonesia, I think. In addition to scrap steel, one alternative raw material iron is iron sand. As we know, in Indonesia there is the long beach, so there is the potential to raw material for iron making from the iron sand. Yeah, because beside the containing the iron is also contain the titanium, so maybe we can spread between iron and titanium. I think is the added value from titanium is also high value. That's why the improvement must be made. That means the make-up standard and advanced scrap covenant to achieve the rational steel consumption, and then the scrap export rule need to be limited, and then the Indonesia need suitable technology to do the iron sand processing. Also the rule that is the environmental friendly. So from this description, we have concluded that the Indonesia steel consumption, which continues to increase each year, is a challenge and opportunity to generate national steel making process that is the environmentally friendly and suitable, also shape the circular economy in the iron and steel sector. And then currently there are several options of iron and steel manufacturing technology that have relatively low CO2 emission, such as smelting reduction technology,
About the iron making overview, we know that this iron making process is quite long establishment technology, but still have opportunity to improve. Yeah, that already shared from Volkswagen by improving the process, by replacing the fuel, yeah, and then etc. That already shared with you from Mr. Sumi. So for the audience, you have already a question to ask for process again. Is there anyone? Okay, Mr. Putu Suwarno.
Thank you, Professor Shungi. So, interestingly, that about this hydrogen, you mentioned about the possibility to use hydrogen
Yes,
as a reduction agent.
reduction engine, yeah.
So, how much of this hydrogen will we need to produce an iron, and does it need to be supplied continuously then? It needs to be supplied continuously, the hydrogen.
Yeah.
And okay, I would like to ask, and is there any special design of this hydrogen pressure vessel that we need?
Yeah.
Then? And also, has it been applied in Indonesia
Yeah.
using this hydrogen?
Yeah.
Okay, thank you very much.
Thank you. So the opportunity of hydrogen in iron making is, I think, it's already applied in the other country. Yeah. So for how much the hydrogen we need, I think it's depend on the capacity. So we can calculate with mass and with balance. So I cannot absolutely predict how much, but we can calculate with mass balance. So how to produce hydrogen? I think it's and it's many technology how to produce hydrogen. So we can use the fuel cell, fuel cell technology, or the other electrolysis technology. So of course we need the hydrogen storage. Yeah. So that means maybe for now, maybe Indonesia there is no company to produce the hydrogen storage, but for the iron steel company, yeah, maybe we can import from the other country. Yeah, but the goal is to reduce the CO2 emission. As we know that the pressure to the CO2 emission is become tight year to year. Yeah.
Thank you.
Okay, thank you for the question. Is there any participant? Raise your hands for Mr. President. Mr. Sungyo, about the policy of the government that our government is open to import steel product from overseas, especially from China. What do you think about this policy?
Yeah, I think we have no choice. So that's why, for the accommodation or researcher, we need to understand the proven technology. Yeah, so that's why what from this one we can improve and modify, or we make the new innovation. So and I hope we can make the technology myself. Yeah.
Is there anyone? We have still 5 minutes left for question and answer. Okay. Dr. Futuhi, please.
Yes.
Thank you so much for the nice presentation. My question is, you suggested different routes for reduction of CO2 emission. Which one you see like a better near-term solution for Indonesia?
Okay.
And which one you see like a more like long-term vision that Indonesia should have?
Okay, thank you for the good question. Yeah, I think from now, I think it's better if we use the biomass, because in Indonesia, as you know, we have the forests in the large area, so that's why it's no problem. If for a while we use the biomass to substitute the coal. Yeah, and then we can continue with using the hydrogen if we ready to understand the technology and how to produce the hydrogen and how to storage the hydrogen. Yeah, it's in my opinion.
Thank you. And I guess one of the areas that also can be looked is about green energy, meaning producing electricity from
Yes.
solar panels or other ways
Yes,
that we
yes.
can reduce.
Yeah, we can combine with the other renewable energy. Okay, thank you.
For biomass, is there any specification for using this process?
Yeah, of course, we have to know the composition, the content of the biomass. Yeah, actually, if we plan to operate, for example, the blast furnace, we have calculate everything. All of the element we need in the blast furnace. Yeah, so, for example, if the CO gas, the content is carbon and oxygen. So that's why for the biomass, we have to know the, for example, content of the carbon and how about the impurities. I think this is the will be effect to the process in the blast furnace.
Okay, thank you very much for your attention. Thank you, Prof. Sungking, for your nice,
welcome.
excellent presentation. We give public applause for Professor Sungking, for the last our speaker today. And then, for the next, I will forward back to Master of Ceremony.
Thank you to Associate Professor Sungging Pintawantoro as the keynote speaker session and Bapak Lukman Nurohim, ST, MSc and PhD for the guiding session excellently as our honored moderator. Thank you as well to the participant for digging deeper and delivering your questions to Bapak Sungging Pintawantoro.
In great appreciation of our keynote speaker, on behalf of the Department of Material and Metallurgical Engineering and the ICOMMET team, Bapak Lukman Nurohim, as the moderator, will present a token of appreciation in the form of a souvenir to our keynote speaker with the help of the committee bringing in the souvenirs.
Please give a round of applause. We hope that Bapak Sungging Pintawantoro had a memorable time at the 5th International Conference on Materials and Metallurgical Engineering and Technology 2022. Once again, thank you Bapak Associate Professor Sungging Pintawantoro for the insights. Let's give another round of applause.
To Bapak Lukman Nurohim, ST, MSc and PhD, thank you for guiding the keynote speaker sessions for today. You may return back to your seat. Let's give a round of applause to Bapak Lukman Nurohim.
Excellencies, we are sorry to inform that due to some problems, there's a 50 minutes of lateness for parallel sessions from the previous rundown. For the next agenda, there will be a parallel sessions. To tell you about these sessions, it will be divided into different rooms, where each room will have an invited speaker who will discuss about a certain topic. The division for the fourth session is as follows. Room 1 is for materials for medical and health prevention applications. Room 2, extractive metallurgy. Room 3, polymer, ceramic and glass, continued by electronic, magnetic and photonic materials. Room 4, materials for energy conversion, transport and storage. And Room 5, advanced materials and nanotechnologies.
Excellencies, the parallel session is going to be as exciting as the main event. But not just machines, even human needs energy to move. So before that, we are going to have a coffee break. You can receive your snacks and drinks on the sides. Please be reminded that the coffee break will end by 11:15 a.m. After you have finished, we are going to have our parallel sessions where you may go straight to the rooms as mentioned before. To the delegates that have finished presenting during the parallel sessions, you may get your certificates at the front desk.
Before the dismissal, we would like to highly encourage distinguished delegates to gain plenty knowledge throughout the event and gain the best result as the awards will be given to the best paper and the best presentation. The selection will be determined by the ICOMMET team.
Since the main session has ended, have a good break and a fruitful session ahead. Please return back to the main venue after the parallel sessions to have the closing and awarding ceremony. Thank you.